Let's go ahead and talk about partial derivatives. And what I would start off by saying is the very kind of general idea here is that you are literally, no, I feel like people say pretend, but like we're not even pretending. We are actually going to assume that one of the variables is being held, and then we're going to ask, okay, great. How is this function changing if we move in the direction of one variable while holding the other variable constant? So let's start off with an example that I really like. We'll start off with a two-dimensional surface, f of xy equal to 9 minus x squared minus y squared. We're going to draw it. This is just an upside down paraboloid. I think I might have drawn it before. I usually draw it by, let me grab some other colored pens here because I'm definitely going to need them all. I think about drawing the downward parabola in both directions. So like, here's my point 0, 0, 9. And then I get a parabola in the YZ plane. I get a parabola in the XZ plane. And I get a circle in the XY plane. Which makes sense if you think about it, right? Because if we set Z equal to 0, right, this is the note here. If we set Z equal to 0, we get 9 minus x squared minus y squared equal to 0. Or in other words, x squared plus y squared equal to 9. A circle of radius 3. And the idea here is that we're going to hold something constant. Oh yeah, I forgot. We're gonna look at one of these points. We're gonna look at the point 1, 2, 4. So if we go, not good. Go 1 in the x direction, 2 in the y direction, and 4 in the z direction. We're gonna end up right about there on the surface. That point there is point 1, 2, 4. It's on the level curve z equal to 4. Looks like everyone's gotten it probably. You can just set it out right there. That's fine. So we're going to take a look at what happens if we move from that point in either the x direction or in the y direction. And let's go ahead and look in the x direction first. So in the x direction, so the point out is that in the x direction, we are holding y constant. Right, we're just going to move essentially forward towards you, which is never the easiest thing to draw. And actually, I'm going to give you some nice pictures in a second. So the idea here is we're going to set y equal to 2, right? Because we're at the point 1, 2, 4. Y isn't going to change. So we're just going to hold y equal to 2, which means our function now is going to look like the following. We're going to get f of x, 2 equal to 9 minus x squared minus 2 squared. Or in other words, f of x, 2 is equal to 5 minus x squared. Just a downward opening parabola, nothing special. So here's what that looks like. Along the line y equals 2, so that's, or I should say along the plane y equals 2, you've got this parabola here. It's doing that kind of thing. And from this point here, so let me ask you all, and I know my pictures aren't the best, but if I was to move in the towards you direction from this point right here, would we be going up the hill or down the hill? Down the hill, right? I'm moving towards you on the slope that's kind of moving down towards you. What that should mean for us is that our partial derivative in the x direction at that point shouldn't be negative because we're essentially decreasing the value of the function as we move in the positive x direction. Right? Just like in 17a, when we take derivatives, when you move from left to right, if your derivative is negative, you're going down from left to right. If your derivative is positive, you're moving up from left to right. So whatever direction you're moving in, either the positive x direction or the positive y direction, if your derivative is negative, you're moving downwards as you go that way, derivative is positive, moving upwards. So here, our partial derivative, which is going to be either written as del f del x or as fx. We really just say fx, we don't say f sub x. The appropriate way to say it is fx, kind of annoying. Not f of x for sure, is going to equal, we're just going to take the derivative here. It's going to be negative 2x. And then if we want to find out the value of the derivative at that point, we're going to plug in the point. So del f del x evaluated at the point 1, 2, 4 is going to be negative 2 times 1, which is negative 2. So that means at that point, if I moved 1 in the x direction, I would move down 2 in the z direction. I'd move 1 forward and down 2 because my slope is negative 2. And I'll draw it here, but then I'm going to show you a better picture. You can kind of think of the tangent line here as looking like that. Let's see some nicer pictures. Here's my surface. And there's the point 1, 2, 4. Okay, see that? Okay, exactly, right? So then let's take a look here. Here's the plane y equal to 2, which is kind of limiting, right? We're just moving in that plane. If we're moving in that plane, we can't move left or right. We can only move forwards and backwards. And we can even look at, what do we got here? Here's the curve I'm looking for, yeah. So if you look at that little blue curve there, there's like the curve of intersection. So that's the curve z equal to 5 minus x squared when y is equal to 2, right? We're definitely stuck with y equal to 2 there. And then here's the tangent line. Can you guys see that okay? Right, so looking at it more easily, right there it is right there. My color's not the best choices. But that tangent line is only moving, right? It's really in the x direction, right? So it's not moving left or right. It's really just going down, down, down towards you. And the slope of that line is negative 2 at that point. And then just to kind of show you what we're going to do next, now we're going to go in the y direction. So instead of holding y constant, we're going to hold x constant. So where'd you go? X equal to 1. So now we're looking at, that little slice of our surface. And here is the curve of intersection. Right, there's your downward opening parabola, which would be something like z equal to 8 minus y squared. We'll write down in a minute here. And then the tangent line at that point is going to look like this. And you can see it's going down from left to right. Or I should say, if we move in the positive y direction, which is to the right, then that graph is going down from left to right. So we have a negative slope again. It's more negative, right? That function is steep, or that slope is steeper there, but similar idea. I mean, just to kind of give you a little perspective there, you can kind of see what's happening there. So then, oops, you go away. Calculation-wise, what we've got here is that if we hold x equal to 1, now we're looking at a whole different kind of thing. You try to not destroy my drawing here. But right there's x equal to 1 right there, if you can see me draw it. And then here's I'm out of colors here. We'll use this color. Here's the parabola that's going along with x equal to 1. And then at this point right here, the tangent line, oof, geez, okay, looks like that. Graphically, if we find del f del y, or fy, well, it's going to equal negative 2y, right? If we look at our original function here, fun fact, you don't even have to plug in the 1 for x. You can, and say, okay, if I plug in 1 for x, I've got 9 minus 1 minus y squared. And then the derivative is going to be, with respect to y, negative 2y. But even if you just leave the x squared there, we can just imagine, oh yeah, x is a constant. It's not going to change. So its derivative is going to be 0, because when something isn't changing, its derivative is 0. Or its rate of change is 0 if it's not changing. So del f del y, or fy, is going to be negative 2y. And if we plug in the point 1, 2, 4, we're going to get negative 2 times 2, which is negative 4. So at that one point, in the x direction, the slope is negative 2. In the y direction, the slope is even steeper. It's negative 4. To sum up, what really matters here as far as actually taking partial derivatives is that whatever we're differentiating with respect to, any other variable gets treated like a constant. That's really the whole gist of partial derivatives. And we'll do some examples for sure, but that's kind of really it. Questions about that before we move on to do more examples? Okay. There is a definition of a partial derivative. I don't really like, he kind of briefly talked about it in class for just like a second, where if you wanted to do it the long way, which you should never really do, but if you wanted to find, say, in fact, yeah, let's do it for this function. So for this function, if I actually wanted to find the partial with respect to x the long way, using the limit definition, well, it's the limit as h approaches 0 of f of x plus h, comma y, minus f of x, comma y, over h. It's really like the same as the limit definition of the derivative, just the thing that's changing gets the plus h, and the thing that's being held constant stays as it was. So here it'd be kind of, it's always annoying to write out, but if you wrote it out, here's what you get. You probably don't need to write this down, but you can certainly. F of x plus h comma y, I'm just going to plug in x plus h for x and get 9 minus x plus h squared minus y squared minus f of xy, which is 9 minus x squared minus y squared, all over h. And now look what happens. What cancels really easily here? What's one thing that cancels super easily? Where you say things. Not a trick question. There's something that really cancels easily. Yes, 9, exactly. What's another thing that cancels really easily? Not yet, but we're almost, but it will cancel. Not x squared, but y, or at least in my opinion, y squared cancels really easily, right? The 9 minus 9 is 0. The negative y squared minus negative y squared, also 0. The x we have to multiply out before we can cancel it. So here's what we're going to get. 9 to go away, y squared to go away. So the limit as h goes to 0. I'm going to multiply this out and get x squared plus 2xh plus h squared. Minus minus is plus x squared all over h. Distribute the minus sign. We've got negative x squared minus 2xh minus h squared plus x squared. And now the x squareds get to add up to 0. And then the rest of the terms have h like we used to look for when we did the limit definition of the derivative back in 17a. Then we can factor out an h, cancel the h in the denominator, and then you've got the limit as h goes to 0 of negative 2x minus h, and then you plug in 0 for the remaining h's, and oh, look, it's exactly what we thought it was going to be. So you certainly could do a limit definition of a partial to find a partial derivative if you were asked to. It's essentially the same as what we did back in the first quarter of calculus, just with a little extra on there. Yeah. So the name of the game here is pretend, or don't, but essentially assume that the thing that isn't the variable of interest is a constant, and then differentiate away like you normally would. So let us look, and we'll get to that. I don't start there. Yeah. So let's look at some examples. For example, let's say we have f of x comma y equal to x to the 4th plus y cubed plus x squared y to the 5th. And not only are we going to take the first derivatives, the first partials, we're also going to take the second partial derivatives. And I think it's actually harder to write them down than it is to find them, but let's do it. So first partials, or just the partials. You should try to become comfortable with both notations. It's usually easier to write the fx notation versus the del f del x, but they're both are good and they're both going to get utilized. You'll see them both in the textbook. So we can either say that fx or del f del x. If you weren't here last week, a reminder that the del here is kind of like the letter D, but it's a little curlier. No one's looking to see if you've written a D or a del, but it is technically incorrect to write a D here. So I'm going to try to write the right notation. So the derivative of x to the fourth is 4x cubed. The derivative of a constant cubed is 0. And the derivative of x squared times a constant is 2x times that constant. Oh, I know what it was. I was going to do something. I was going to, yeah. Let me go back just a little for a moment, just so I can say one more thing before we'll continue with this. But I just want to say one more kind of guiding principle here, just to make sure everyone's on board. If you have a function like cosine of x plus 6, what's the derivative of that? I know it's been, what's the derivative of cosine again? Negative sine of x plus, right. On the other hand, if my derivative is 6 times cosine of x, sorry, if my function is 6 times cosine of x, what's the derivative going to be? Right. So the point being, which I've already alluded to a few times, is that if you have a constant by itself, its derivative is 0. But if you have a constant multiplying a function of the variable of interest, that constant multiple hangs out, as I like to say. Yeah. The front lights are off. So I think if I turn the other lights off, I think we are in the dark. Let's see here. It's kind of a little dark. I mean, I know that looks better, but it's a little dark for my taste, unfortunately. That's not better at all. That is not great though. Let's see if I can do anything over here. Is that better? Okay. It turned up a little bit before, but I should just yeah. Okay, that's better. Yeah, I wish we could turn off like all but the last row, but I don't think that's possible, unfortunately. So constants on their own, derivative of 0, constant multiples hang out. So like we saw here, this constant that's on its own, right? It doesn't have any x's attached to it. Its derivative is 0. Whereas this constant y to the fifth, it's multiplied by a thing with a variable. So the y to the fifth gets to stick around, multiplied by the derivative of x squared, which is 2x. I would, of course, simplify this and write it as 4x cubed plus 2x y to the fifth. In a similar way, the partial with respect to y, which is del f del y, now we flip the script and we treat x as a constant. So x to the fourth is like 2 to the fourth, whose derivative is 0. The derivative of y cubed is 3y squared. And the derivative of this constant times y to the fifth is x squared times 5y to the fourth. And again, I would simplify this just a touch and write it as 3y squared plus 5x squared y to the fourth. It's pretty standard to write constants out in front of the whole thing. Actual constants out in front of the variables. There's also second partials. So we should say, yeah, so we'll do the second partials or second partial derivatives. So we have fxx or del squared f del x squared. Really, this means is you're taking the derivative with respect to x again. So this is, I'm going to write it one more time or one more way. It's del x of del f del x. We already know what del f del x is. It's written on the page. So this is the partial derivative with respect to x of 4x cubed plus 2xy to the fifth. And then we just apply the rule. Now, no, I'll point out, normally you wouldn't write all this. What you would really do here, if you were doing this efficiently, is you would look at that and then say, okay, the derivative of 4x cubed with respect to x is 12x squared, and the derivative of 2x times y to the fifth is going to be 2 times y to the fifth. I'm just kind of writing all this out so you can see the notation a few times. Similarly, fyy, the second partial with respect to y, or del squared f del y squared, which is del y of del f del y, which is del y of 3y squared plus 5x squared y to the fourth. And really, really genuinely, you should skip all of this crap I just wrote and go straight from fyy to, great, look at this, it's equal to that, take the derivative with respect to y. The derivative of 3y squared is 6y. The derivative of 5x squared times y to the fourth, the 5x squared hangs out. And the derivative of y to the fourth is 4y cubed. And then, yes, I would simplify that as 6y plus 20 x squared y cubed. It's pretty standard fare when we're talking about partial derivatives to ask for the first partials, the second partials, and the mixed partials. So the mixed partials are when you do the derivative with respect to x and with respect to y. So I should say you do one of each in either order. So let's write them both down. I don't really feel like I have enough room here, so let's not try to squeeze things in. Try to be better about not writing tiny things on paper. So the mixed partials. This is where the notation is kind of terrible. And I am going to write it all out so you can see it. So you can either say, let's go that way first. So you can either say it's, yeah, let's do that. fxy, which means you do the derivative with respect to x first, and then the derivative of that with respect to y second. Looking for a different pen. Sorry, I'm hiding my pens from myself. Fine, just be that way, pens. Where'd you go? I should like label these better. So when you write this, it means x first, y second. Here's how you write it with the Leibniz notation. It is equal to del squared f del y del x. That means x first and y second. So with the Leibniz notation, you read it from right to left, essentially. Because what this really means is it's the partial with respect to y of the partial with respect to x. X, holy smokes, James, you have to write the right letters if you want to get the right point across. Sorry about that. So this means here, it's the derivative with respect to y of the partial with respect to x that we found way up here. So it's the partial with respect to y of 4x cubed plus 2xy to the fifth. The partial with respect to y is going to be, well, that part's going to be 0, because the derivative of 4x cubed with respect to y is 0. And the derivative of this is going to be, the 2x is going to hang out, and the derivative of y to the fifth is 5y to the fourth. Simplifying, we get 10xy to the fourth. And again, I normally wouldn't write all this, and I won't in the future problems, but I would just point out that, right, what we're doing is we're just saying, okay, do the derivative of your original function with respect to x first. Great, I got 4x cubed plus 2xy to the fifth. Then look at that and do the derivative with respect to y. Oh, the derivative of 4x cubed is 0 with respect to y. The derivative of 2xy to the fifth is 2x times 5y to the fourth. Now let's do it in the opposite order. So instead of doing x first, then y, we'll do y first, then x. So if we want to find fyx, also written as del squared f del x del y, which is del x of del f del y, which is del x of our partial with respect to y. I don't have it written in front of me, so I'm just going to look up here and take the partial. So let's actually do it the way I would do it. So the partial of this with respect to y is 0, which I'm not going to write down, plus 3y squared plus x squared times y to the fifth, which is 5x squared y to the fourth. And if we're going to differentiate that with respect to x, we're going to get 0 from that first term and a 10x times y to the fourth. And I don't remember the words your teacher wrote specifically, although I did write them down. Yeah. So while it is not generally the case the mixed partials are equal to each other, what that means is they aren't always equal to each other, but most of the time they are. In fact, in this class, it is almost always the case that the mixed partials, whichever way you calculate them, will always be the same either way. So these are usually the same. I should show you this example. So just to maybe, what's the word? The word I want to use is to assuage any fears. So just in case you're worried about like, what if we have a function where they're not the same? Let me show you real quick here what most people consider to be the easiest example of a function where the mixed partials are not equal to each other. If I can find it real quick here. Sorry, 1 second. It's not an easy function to just remember. So let me show you what I mean. Yeah. You do your thing here. Sorry, where'd you go, cursor? So let's look at Grant's very useful website. Yeah, we don't do anymore. Let's go to Co-17C. I think this example is down here. Is it not down here? Partial derivatives. Maybe not. Where else would it be? Sorry, 1 second. Apologies. Maybe it's in the 21C stuff. Darn it, I've forgotten where it is. Oh, I think it's right here. Oh, differential. Sorry. I really do want to see, just because I really want you to be like, you shouldn't worry about this because it's not that big a deal. Let's see if it's any one of these things here. Sorry, I should have prepared for this ahead of time, but it wasn't. That's the same thing I already looked at. That's that. No. It could be this one. Yes. So, although this isn't showing it, but I'll tell you this function right here, this piecewise function that's equal to x squared times y squared over x squared plus y squared when xy isn't the origin and is equal to 0 when x is the origin. This is an example of a function where the mixed partials end up being not equal to each other. Like the mixed partial in one direction is equal to +1, and the other order is equal to -1. And this is often the least complicated example of a function where the mixed partials are not equal to each other. So what I want to point out is if you have a function that looks, for lack of a better word, normal, right? Like I would say this looks like a normal function, right? We've just kind of written like things with x's and y's. It's not piecewise. There's nothing funky going on here. It is almost always the case that your mixed partials are going to be equal to each other. So you shouldn't worry about that unless someone specifically says you need to worry about it because it's generally true. All right, let's look at some more examples. Sorry, if I can move the papers here. So let's say we have something like f of xy equal to tangent of x squared plus y cubed minus e to the x y. Looks relatively annoying here. Let's start finding some partial derivatives. So if I was going to find the partials, I would do it this way. Partial with respect to x. Well, again, I'm treating y like a constant. So I've got tangent of some stuff. The derivative of tangent of some stuff is secant squared of that stuff. And then I have to multiply by the derivative of the inside stuff, which is going to be 2x plus 0. not going to write the plus 0. Minus the derivative of e to the something is e to the something times the derivative of the something. So the derivative of e to the xy is going to be e to the xy times the derivative with respect to x of xy, which is going to be 1 times y, or just y. Let's go the other. In fact, why don't you all do the next one? So find the partial with respect to y. I'll give you like a minute. I do, yeah. Somewhere. Okay. Go. You can, that's fine. Okay.
Thank you.
You're welcome. So let's take a look and see what we got. Again, the derivative tangent of some stuff is still secant squared of that stuff. Now, when we differentiate the argument of the secant squared function, the derivative of x squared plus y cubed with respect to y is going to be 3y squared. And the derivative of e to the xy is going to be, whoops, minus e to the xy. And then we multiply by the derivative with respect to y of x times y, and we get x times 1. And then the second partial will start to get really messy. In fact, maybe messier than I want to deal with. But we'll take a look. Okay. Papers all over the place here. So start looking at second partials, fxx. So again, I'm looking at fx. I'm just thinking about taking the derivative of that with respect to x, which is going to be kind of gross. So I'll point, let's write this, I'm going to make sure that you recognize here that when you take the derivative of secant squared of some stuff, I'm really thinking of that as secant of x squared plus y cubed quantity squared times 2x minus e to the xy times y. So when we take the derivative of this squared, it's going to be chain rule upon chain rule. So it's going to be 2 times secant of your stuff to the first power, which I'm not going to write, times the derivative of the inside of that first power, which is the derivative of secant of your stuff. So the derivative of secant of x squared plus y cubed is secant of your stuff times tangent of your stuff times the derivative of your stuff, which is 2x. All of that multiplied by the 2x that's chilling over there. So there's the first part of your product rule. And then we have to still add on this times the derivative of that. So secant of x squared plus y cubed squared. Sorry, that y cubed should be inside the parentheses there. That is a terrible mistake I should never be forgiven for. Times the derivative of 2x, which is 2. Finally, the derivative of e to the xy times y is going to be, well, the y hangs out because it's a constant, and the derivative of e to the xy is, again, e to the xy times another y. So it's e to the xy times y times y. Kind of gnarly. The good news is taking the other partial, the other mix, the other second partial at FYY will be pretty much the same work, so we can probably figure it out without so much mental effort. Let's look at FYY here. So I'm looking at this now, and then I want to take its derivative. So I should have said last time, and I didn't. When we do this derivative of secant squared of x plus y cubed times 3y squared, we do have to use the product rule because it's a function of y times another function of y. So it's the derivative of this piece. Okay, great. We saw last time that the derivative of secant squared of some stuff is 2 times secant of your stuff times secant of your stuff times tangent of your stuff times the derivative of your stuff. Ugh, gross. You get 2 times secant of x squared plus y cubed times secant of x squared plus y cubed times tangent of x squared plus y cubed. But now the derivative we have to multiply by is 3y squared. All that times 3y squared. So it's like we did the derivative of this multiplied by 3y squared. When we switch things up, we leave the secant squared of x squared plus y cubed alone. We multiply by the derivative of 3y squared, which is 6y. Finally, we take the derivative of e to the xy, which is e to the xy times x. And then the other x is just hanging out. Which, yes, a normal person would write e to the xy times x squared. I just was trying to show that we're getting an extra x showing up there. Kind of funky. Maybe a little bit much. That's why I was doing that one. Let's do one of the mixed partials. So they both kind of suck. Let's go ahead and find fxy. I mean, they both are going to be the same. So after I do this, you all should take some time on your own later on and do it the other way. So fxy, I'm looking at fx here. I'm going to take the derivative of that with respect to y. So I don't have to use the product rule here anymore. It's just going to be the derivative of secant squared of x plus y cubed with respect to y. Okay, it's still gross. It's still going to be all that gnarliness right there. It's going to be 2 times secant of x squared plus y cubed times secant of x squared plus y cubed times tangent of x squared plus y cubed. But then the derivative of the inside we're going to multiply by is the derivative of the y cubed part. So it's 3y squared. And then multiply by 2x. So that's the derivative of this piece right here. And then for the e to the xy times y, we are going to have to use the product rule because it's a function of y times another function of y. So we're going to get minus the derivative of e to the xy with respect to y. So e to the xy times x times the other function y. Plus, then we switch it up. We leave the e to the xy alone. Multiply by the derivative of y, which is 1. So you can see that higher order derivatives really can spiral out of control really quickly if the function is even a little bit funky. Let's look at a less terrible example. Yeah, we got time. So on your own, when you have a chance, find fyx and show that it's the same. All right. So most of the time in this section, we're going to be dealing with functions of x and y. But not every multivariable function has to be like z equal to some function of x and y or just f of x, y. You could have functions of 3 or 4 or 20 variables if you really wanted to. Usually we don't go much higher than 3. So let's say, for example, let me use words. So we can take partials or partial derivatives of functions of more than 2 variables. For example, f of x comma y comma z equal to x cubed times sine of 4y plus z to the 6th. And really the story is you can take any number of partials you want in any order you want. So we almost always start with like the first partials. So we could find fx. So as far as x is concerned, I only see an x here. So everything else here, as far as we are concerned at this moment, is a constant. And the derivative of x cubed times a constant is 3x squared times that same constant. If you have questions, please ask them. Let's look at the partial with respect to y. So now, if we look at this original function, I'm seeing x cubed, which is now a constant in my brain. I have a constant times sine of a variable. So this is the functional part. This is the constant part. The x cubed gets to hang out. And the derivative of sine of some stuff is going to be cosine of that stuff times the derivative of the inside stuff. So I'll point out here, it's kind of important here. When we take the derivative of sine of the stuff here, you get cosine of that stuff just stays as is, right? It's going to be cosine of 4y plus z to the 6, but then we're going to multiply by what? Show me on your fingers. What are we going to multiply by? Right, the derivative of 4y plus z to the 6, which is 4 plus 0, if you want to say plus 0. Why don't you all find the partial with respect to z? Yeah.
Class, that's referring to second partial?
Or higher even. We're going to go higher than that in just a second. But yes, yeah, a second partial is a higher order. So it's a mixed partial. Essentially, if you're doing more than one partial derivative, then it's a higher order partial derivative. It's almost the same. The partial with respect to z is x cubed times cosine of 4y plus z to the 6. But instead of multiplying by 4, now the derivative of the inside, since we're differentiating with respect to the variable z, is going to be 0 plus 6z to the 5th. I should point out that when people say mixed partials, they generally mean specifically the two we talked about before, either fxy or fyx, or del squared f del x del z, and del squared f del x del y, or del y del x. But the mixed partial can actually really be any number of derivatives that you take one after another. So for example, we could say find f x y y, which means we would do the derivative with respect to x first, and then y again, which I don't really want to, but you could certainly write as, oh, it's annoying, del cubed f del y squared del x, which means you're doing x first and then y again. Gross. Either way, so the problem here is that you kind of don't just write this out. So I'm not going to do it all at once. So I can't do two derivatives at a time, essentially. Right? I can only do one derivative at a time. Right? Like I can't go from a function to a second derivative without going through the first derivative. So here, we're first going to take our fx, which you already know is that. I shouldn't even write it down. And let's find fxy. So we're going to take the derivative of fx with respect to y. So it's going to be del y of our 3x squared times sine of 4y plus z to the 6th. So great, the 3x squared gets to hang out. And the derivative of sine of some stuff is going to be cosine of that stuff times the derivative of the inside stuff, which is just 4. Because again, 4y is the variable, and plus z to the 6 is the constant in this segment. And it does, I mean, it's not a huge deal here, but I would take the moment to simplify it, because if I'm going to take another derivative, it's usually going to be a good idea to make the thing you're differentiating as nice as possible. Okay, so now we find f x, y, y, we're just going to take the derivative of that with respect to y again. So the 12x squared still gets to hang out. And the derivative of cosine of some stuff is going to be negative sine of that stuff multiplied by the derivative of the inside stuff, which again is 4. I happen to make a smart choice here where things didn't get too complicated too fast. So we're going to get, let's see, if I simplify this, a negative 12 times 4 is negative 48 x squared times sine of 4y plus z to the 6th. Here's a good question. What if instead we've been asked to find f, x, y, x? Or if you prefer, which you shouldn't prefer because no one prefers, del cubed f, del x, del y, del x. I find this notation especially confusing because this means x first, y second, x third. And watch out here, watch for a second. This means x first, y second, x third. So you're still doing, and it still looks the same if you flip it out, but it's right, it's backwards. I'm not trying to be confusing on purpose. I'm just trying to point out that this notation is backwards of that notation. But here, since it's the same, whether you write it as xyx or as xyx, it looks the same. Don't do too much work. I've already done 2/3 of the work for this problem. So I already know that fxy is that. So my fxy, I'm just going to write it again, is 12x squared times cosine of 4y plus z to the 6th. I want to find fxyx, so I'm going to take the partial with respect to x of that. fxyx is equal to, well, that's all a constant as far as x is concerned. The derivative of 12x squared is 24x. And then the cosine of 4y plus z to the 6th just hangs out. And I would say, in a similar way, you all could easily find the partial fxy, I should say the mixed partial fxyz. Should be del cubed f del z del y del x. But again, I should really just look at fxy and then take the derivative of that with respect to z, which is going to be a little less nice than this one, but still not that bad. The 12x squared hangs out. The derivative of cosine of some stuff is negative sine of that stuff. And then I multiply by the derivative of the inside, which in this case would be 6z to the 5th, which I feel bad about squeezing in here. So, all the things I've said today, long story short, when you're finding partial derivatives, whatever isn't the variable of interest gets to pretend like it's a constant, and then the variable that you're differentiating with respect to, that's the thing you take the derivative of. Is that a question or just a stretch? Okay. So really, when you're finding partial derivatives, you still have to use, product rule, chain rule, maybe the quotient rule, whatever rules apply. But just remember, you're only thinking of, if it's the partial with respect to x, you're only thinking of the x's as variables, and any y or z or anything else gets to pretend like it's a constant for that moment. And then when you switch it to something else, then you have to switch your way you're thinking of everything else. So it's easy once you do it a few times, but it does take some getting used to. All right, that is all we've got for today. Wednesday, I think we'll talk about tangent planes, linearizations.